Hi everyone, this is Mrs. Moz, and this is the test review for Forces in Motion, which is your purple note packet. I just wanted to quickly point out the flashcards for Section 1 and 1.5, and for Newton's Laws and the unit flashcards are all on Schoology. You just click on Schoology, click on your physical science class, click on the purple folder that says Forces in Motion, and then there's a folder that says Study Materials, and you've got a couple PDFs you can print off, or you can just look at the ones on your screen. Maybe you want to take a picture with your phone, and you can use those to study from. I'm just going to go through a couple problems working from the beginning of your notes through the end. The first ones we're going to look at are how to calculate velocity or gravity or time using three of our equations. So the first question says, a ball at rest is dropped. Now it should say what is the ball's velocity after falling for 4 seconds. Now we're looking for the velocity, so I picked the first equation, and the first equation is delta V equals gravity times time. And delta V means final velocity minus starting velocity. But if the ball is initially at rest, that means its starting velocity is 0. So we're just going to find the final velocity. So our equation is delta V equals gravity times time. Now we know on Earth that our gravity is 9.8 meters per second, and we know that time is 4 seconds, so you take 9.8 times 4. And delta V, or velocity, is always in meters per second, and you also have to have a direction, so if you drop something you know it's going down. And 9.8 times 4 is 39.2 meters per second down. The second problem is looking at that same image, and it says a feather is dropped, and its final velocity is 8 meters per second down. Now I don't tell you the starting velocity because you should already know that if you drop something that its starting velocity is 0. So the delta V is final minus starting. You take 8 minus 0, which gives you 8 meters per second down. Gravity is 9.8 meters per second. How much time will it take to reach the floor? So we're looking for time, which means we're using the second equation. So T equals delta V divided by G. And delta V equals 8 because 8 minus 0 is 8 divided by 9.8 for gravity. And that should give you 0.82 seconds. Our next problem says a phone at rest is dropped. What is its velocity after falling for 0.25 seconds? So looking for velocity, once again, we're going to use the first equation. So delta V, or delta velocity, equals gravity times time. Gravity on Earth is always 9.8 meters per second. Time is 0.25 seconds. Multiply them together and you should get 2.45 meters per second down. Remember that velocity is always speed in a specific direction. That's why I'm including a direction for every single one of my problems. The second question is, a cat at rest falls and its final speed is 4.4 meters per second. Gravity equals 9.8 meters per second. How long does it take to hit the water? When I'm asking for how long, I'm looking for how much time does it take before the cat will hit the water. I'm looking for time. Time is the second equation because it starts with a T. So T equals delta V divided by G. My delta V is the final velocity minus starting velocity. So final velocity is 4.4 meters per second. If you look at the picture, you see that the cat is just standing on the ledge of the bathtub. So its initial velocity is 0. So you take 4.4 minus 0, which should give you 4.4 meters per second, divided by gravity, and gravity is 9.8 meters per second. So you should get time equals 0.45 seconds. Our next problem deals with a watermelon being dropped, and we want to know what is its velocity after falling for 6.2 seconds. So we're looking for velocity. Velocity is the very first equation. Delta V equals gravity times time. And we're going to take 9.8 meters per second times 6.2 seconds, which should give you 60.76 meters per second down. Second problem, a toy traveling at 4 meters per second speeds up to 17 meters per second in 1.33 seconds. What is gravity? Now this is the first time we've looked for gravity, but you approach it the same way as the other problems. Gravity starts with a G, so you're looking for the third equation. Gravity equals delta V divided by time. This one is a little bit more complicated because it does not say that the toy dropped is starting at rest or starting at 0. So you have to really think, which one is the final velocity? It says a toy traveling at 4 meters per second speeds up to 17 meters per second. So we know 17 meters per second is its end or final velocity, and 4 is its starting velocity. So what I'm going to do is take 17 minus 4, which should give you 13 meters per second, all divided by time, and time is 1.33 seconds, which should give you 9.8 meters per second per second. And a way you can double check your answer for this one is that gravity on Earth, or acceleration due to gravity on Earth, is always 9.8 meters per second per second. On a test or a quiz, you cannot assume that all of the problems will be dealing with Earth, so you should just double check your math. Okay, similar to the last question, just I changed the numbers a little bit. A watermelon at rest is dropped. What is its velocity after falling for 12.6 seconds? I'm looking for time. Time is the second equation, so use T equals delta V divided by G. Delta V, or final minus starting velocity, equals 9.8 meters per second for gravity, and time is 12.6 seconds. And delta V equals 123.48 meters per second down. The second problem says a toy traveling at 2 meters per second speeds up to 9 meters per second in 5.2 seconds. What is gravity? Gravity starts with a G. We are looking for the third equation. Gravity equals delta V divided by time. And G equals, we have to take the final velocity minus starting velocity, and the final velocity is 9. The starting velocity is 2. 9 minus 2 is 7, divided by 5.2, should give you 1.35 meters per second per second. Now, this one, like I said on the last problem, similar to this, it does not have 9.8 meters per second per second. So we can assume that this toy is not on Earth. It has to be on a different planet. All right, this one I'm just going to walk through instead of doing on the PowerPoint, so you'll have to listen carefully. For projectile motion, this is one that the term is in your notes. Projectile motion is anytime you throw an object and it has a curved path, because it has a vertical and horizontal component, meaning it will move down and it will move side to side at the same time. So the first question says, ball 1 is dropped and takes 8 seconds to reach the ground. What is the velocity of ball 1 before it is dropped? Now, if you think about holding a ball in your hand, the ball should not be moving. So initially, number 2, its velocity should be just 0 meters per second, and it should be down because it needs a direction. Number 3 says, what is the velocity of the ball when it hits the ground? Now, when it hits the ground is its final velocity. So we're going to use the delta V equation. We're going to take delta V equals gravity times time. You can assume that this is on Earth, so we're going to take 9.8 times 8 seconds, and this would give you that its final velocity is 78.4 meters per second down. Number 4 says ball 2 is thrown from the same height and thrown horizontal to the ground. What is the downward velocity of the ball before it is thrown? Similar to ball 1, you're holding it in your hand, so it has to have a velocity of 0 before you throw it. Number 6 says, how many seconds will it take this ball to the ground? If it was dropped from the exact height as ball 1, the horizontal and vertical components of projectile motion can be thought of as separate components. So even if it's thrown perfectly horizontal, it will still hit the ground at the same time as ball 1. So we're just going to use the information from number 1, that it should take 8 seconds. So that was the answer for number 6. It's 8 seconds that it will take to hit the ground. Number 7 says, what is the downward velocity of this ball when it hits the ground? I'm only looking for the downward velocity, not how fast it's moving from left to right. So I'm going to do it the same way as the number 3. So you're looking for delta V. Delta V equals gravity times time. You're going to take 9.8 times 8 seconds again, and you should get the same answer, that it's 78.4 meters per second down. Okay, and we just had a couple examples of inertia in your notes. If I were you, I would take a look back at your notes to refresh yourself. The GIFs don't work when I present, but you can always ask questions if you don't understand in class. Okay, I've got a couple practice problems for inertia. Now, something to keep in mind, inertia is the tendency of an object to resist a change in motion, meaning an object at rest wants to stay at rest, and an object in motion wants to stay in motion. So there are two pieces to inertia. The one that we look at in class is mass. And if you have more mass, you have more inertia. If you have less mass, you have less inertia. So what I'm comparing right now is that you have a football player and a child running at the exact same speed, which is unlikely, but we're just going to go with it. Obviously, the football player has a bigger mass compared to the child. So my question is, which one has more inertia? The answer for that would be that it is the football player, because he has more mass. Second question says, the bowling ball and beach ball are rolling at the same speed. So which one has more inertia? The one that has more mass, and a bowling ball is quite a bit more massive than a beach ball. Okay, similar to the last questions, it says which has more inertia? If both chairs are rolling at the same speed, which one would have more inertia? Now we know that if you have a person sitting in a chair together, it has more mass, and so it would also have more inertia, meaning that if it was rolled towards you, the one with the person sitting in it is more difficult to stop because it does not want to change its motion. That's the definition of inertia. The second example is something we did in class where you take a flashcard, you put it on top of a cup, and you have a penny. If you pull the index card out really quickly from underneath the penny should drop directly into the cup. So my question is, why does the penny drop into the cup and not travel with the index card? The reason is that even though you're moving the index card, the penny itself is at rest to begin with. So it has a velocity of 0, meaning it wants to stay at a velocity of 0. It does not want to move. Now if you pull the index card out, the penny wants to stay in air. However, it will drop down into the cup due to gravity. This is a starter we had in class. So you've got a motorcyclist and he's riding on his motorcycle. And my question is, why does the person keep moving forward? As you can see, he tumbles quite a bit even after he's not on his motorcycle. The reason for that is that he is moving when he's on his motorcycle. Even when he crashes, you can notice that both him and his motorcycle, since they are in motion, they want to stay in motion. If you look at the entire clip, you'll notice that he does eventually come to a stop. The reason for that is that there is friction between him and the ground below him that resists or opposes motion, and that's why he will slow down eventually. Okay, moving on to Newton's second law of motion, there's two things that acceleration depends on. The acceleration of an object depends on the mass of an object, and it also depends on the force. And the easiest way to remember this is that if I were to calculate acceleration starts with an A, so we're looking for the equation that starts with an A, which is A equals F divided by m. The two letters in that equation are what acceleration depends on. So it depends on force, which is F, and mass, which is m. Now you have two different shopping carts. The first shopping cart has a ton of mass in it. It's very full. And the second shopping cart does not have anything in it, so it has a smaller mass. And my question is, if we want them both to be moving with the exact same acceleration, so moving at or speeding up at the exact same rate, how can I get them to accelerate at the same rate even though they have different masses? Now the answer for that is, you can even see this in the picture. The boy is pushing the cart that has more mass with a bigger force, and the one that has less mass, he pushes with a smaller force. And I do a little bit of math to prove this. So let's assume that we want the acceleration to be at least 5 meters per second. The starting mass, or the shopping cart that's full, we're saying the mass is 20 kilograms. The empty shopping cart, we're saying the mass is 4 kilograms. Now if we calculate force equals mass times acceleration. So we take 20 times 5, and that should give you 100 newtons, which is a very, very large force. The shopping cart on the bottom has a mass of 4 and acceleration of 5 meters per second. Force equals mass times acceleration. We're going to take 4 times 5, and that only gives you 20 newtons. Now if you compare, the force on the top cart has to be bigger than the force on the bottom cart in order to get the acceleration to be the same between those two carts. Now force is not the only thing that acceleration depends on. Remember that mass is the other component of the acceleration equation. So we're going to see how mass impacts its acceleration. If you look at the carts, you have two carts, and this time they're both empty, meaning they both have about the same mass. Now the top cart, we have him pushing with a force of 100 newtons, and the bottom cart, we only have him pushing with a force of 20 newtons. So if you push harder on a cart that has the same mass, you would assume that his acceleration would be greater. So we'll prove this. Calculate his acceleration. Acceleration equals force divided by mass, so 100 divided by 4 is 25 meters per second, which is incredibly fast, and humans cannot move at that speed. The second problem, his force is 20 newtons, so he's pushing with only a fifth of his force from the first problem. So we're going to take acceleration equals force divided by mass. We're taking 20 divided by 4, and that's only 5 meters per second. So you can clearly see between these two problems that if you push less or you have a smaller force, your acceleration should also be smaller. So we're going to calculate a couple of these, just practicing using which equation we should pick and how to do the math and what the units are. So before we do that, we're just going to quick run through what the letters mean. F stands for force, and it's always going to be in newtons because Sir Isaac Newton was the one who developed the idea of forces. Then we're going to look at M, and M is mass. Mass is always in kilograms, and the reason for that is that newtons is actually kilogram meters per second squared, or kilogram meters per second, but we just call it newtons because it's a lot easier to say. Acceleration is A, and it's always meters per second, because it's how fast you speed up every second. The first one we're going to calculate is the force of a 9.07 kilogram watermelon falling to Earth, where acceleration equals 9.8 meters per second. So if you look at this problem, it says calculate the force. Force starts with an F. We're looking at our first equation. Force equals mass times acceleration. The mass is 9.07 kilograms, and the acceleration on Earth is 9.8 meters per second. So your end answer should be 88.89 newtons. And newtons you could also have kilogram meters per second, or kilogram meters per second squared. Now the direction of the force, if you look at this picture to the left, it is falling down, because if you drop anything, it should go down due to gravity. And a couple more examples. It says calculate the force of a 7.25 kilogram cat falling to the Earth where acceleration equals 9.8 meters per second. Once again, we're looking for force. Force starts with F. We're looking at the first equation, F equals m times A. Mass is 7.25 times 9.8 for acceleration. And you should have a force of 71.05 newtons. And if you look at the picture, the cat is obviously falling down, so that is our direction. The second question says, what is the acceleration of a 7 kilogram mass if a force of 68.6 newtons is used to move it toward Earth? So this one we're looking for something different. We're looking for acceleration. Acceleration starts with an A. A equals F divided by m. That's our third equation. And force in this equation is 68.6 newtons. Our mass is 7 kilograms. We're going to take 68.6 divided by 7. And that gives us 9.8 meters per second, which is fairly obvious if you assume that it was on Earth, which I gave you in the problem. What's the direction of the force? Drop anything, it will go down. Next question has to do with a phone being dropped. It says the phone is 0.122 kilograms and is accelerating toward Earth at 9.8 meters per second. Now it's very important that when you calculate this, you keep the decimal in the problem, because if you take it out, your answer will be wrong. We want to know what is the phone's force. Force starts with F. We're using the first equation. F equals m times A. The mass is 0.112 kilograms. The acceleration is 9.8 meters per second. And if you multiply those, you should get 1.1 newtons down. You do not have to have a direction for force, but I like to include it on there just in case you had questions later and wanted to look back at your problem. Our next question deals with a car. A car is 770 kilograms and is accelerating left at 12.2 meters per second. What is the car's force? Force starts with F. F equals m times A. Mass equals 770 kilograms times acceleration, which is 12.2 meters per second. And you should get a force of 9,394 newtons left. We got a bowling ball in our next problem, and it says a 13 kilogram bowling ball is thrown and hits the pins with a force of 25 newtons. What is the ball's acceleration? So we're looking for acceleration. Acceleration starts with A. A equals F divided by m. Force is 25 newtons divided by 13 kilograms. And your answer should be 1.92 meters per second. A car is 770 kilograms and crashes into a stop sign with 512 newtons. What is the car's acceleration? We're looking for acceleration. Acceleration starts with A equals F divided by m. Force is 512 newtons. Mass is 770 kilograms. You should get 0.66 meters per second per second. We got a similar problem to last time. This is with a bowling ball. It's thrown and it hits the pins with a force of 25 newtons and is accelerating at 3 meters per second per second. We want to know what is the ball's mass. If you're looking for mass starts with m, so we're looking at m equals F divided by A. The force is 25 newtons. The acceleration is 3 meters per second, and you should get 8.33 kilograms. A car crashes into a brick wall with 512 newtons of force and is accelerating at 2 meters per second per second. What is the car's mass? Like the second problem, we are using mass. Mass starts with an m. M equals force divided by A, or acceleration. So the force is 512 newtons. Acceleration is 2 meters per second, and you should get 256 kilograms. So we finished talking about Newton's first and second laws. Newton's third law we did not do any math for, but you just need to remember that for every action there is a reaction. That reaction is always equal and opposite in direction. So say a rocket is going left at 5,000 newtons, there's an equal and opposite reaction, meaning there's 5,000 newtons going right. So if you want any extra practice on Newton's third law, you can look up the flashcards on Schoology. They're under the folders that I mentioned at the beginning, and you can print those off. Our last topic that we went through was talking about momentum, and momentum is just a measure of motion. And we always find momentum by looking at its mass and its velocity. Momentum has different units than anything we've learned about before. Its units are kilogram meters per second. The reason it's kilograms is because we take mass, and kilogram is the unit for mass, and meters per second is the unit for velocity. So it's kilogram meters per second. It is not kilogram meters per second, or kilogram meters per second squared, because technically that is the unit for force. It's a newton. We just call it newtons though. A really important thing to remember when we talk about momentum is that we cannot use m for momentum because m has already been taken for mass. So we have to use a new letter. They chose p. P equals momentum, and it equals mass times velocity. M is for mass, V is for velocity. Another important piece to remember is that between momentum and mass and velocity, they have a direct relationship, meaning that if mass goes up, momentum goes up. If you decrease your mass, your momentum also decreases or goes down. If you speed up or your velocity goes up, momentum will also go up. If you were to slow down or your velocity goes down, momentum will also go down. So you have a couple practice problems here. Like I said in the last slide, if you increase someone's mass, their momentum goes up. If you increase their velocity, their momentum goes up. So in these two pictures here I have Michelle Kwan. And Michelle Kwan, in both of these pictures, is only about 5 minutes apart. Now we assume that if you're ice skating, your mass is not going to change. Now she may have perspired a little bit, so her mass maybe have changed slightly, but not anything that would be noticeable or change our mass too much. So we're assuming that her mass stays the same at 49.02 kilograms. In the first picture, she's traveling at 2 meters per second. And in the second picture, this is after she has done her skating, she's just simply standing. If you're standing and you're not moving, your velocity is 0. So my first question says, in which of these pictures does Michelle Kwan have more momentum and why? Now we know she has more momentum in picture 1. And the reason for that is that she has a bigger velocity than in picture 2 because her mass has also stayed the same. So the answer is number 1, she has more mass. For B, it says what is Kwan's momentum in each? And if we're looking for momentum, be careful. Momentum does start with an m, but remember m is mass, so we can't use the second equation. We're looking for the first one, where P equals m times V, because momentum is P. So how to do the math for question 1, we're going to take P equals m times V. Her mass is 49.02 kilograms and her velocity is 2 meters per second. You multiply those and you should get 98.04 kilograms meters per second. Now, if you notice, on my unit, I did have it just kilogram meters per second. I do not have a dot. I do not have a multiplication sign, and that's okay. Like I said before in class, you don't have to have a symbol between. If two things are right next to each other, you don't have to say they're multiplied. You immediately know they're multiplied. But you can keep a multiplication symbol in there. It will not be marked wrong. So we're working on calculating her momentum in question 2. Looking for momentum again, momentum is P. So we're looking at the first equation. P equals m times v. Her mass is the same because she's the same person. Her mass does not change. It's 49.02 kilograms. Her velocity is 0 meters per second. Now, if you multiply any number by a 0, her momentum is also 0 kilogram meters per second. So if you look at this problem, you can answer the letter A after you do the math. So in this problem, her second momentum, or her momentum in picture 2 is 0, and her momentum in the first problem was 98.04. So obviously 98.04 is a bigger number than 0. That's another way you can prove to me that her momentum is larger in picture number 1. So similar to Michelle Kwan, we're looking at Usain Bolt. It says, in which of these pictures does Usain Bolt have more momentum and why? Similar to Michelle Kwan, these pictures were only taken moments between the race, before and after. So we're assuming that Usain Bolt's mass has not changed noticeably. Now, like I said, he may have perspired, but we're assuming that it stayed relatively the same. So in question 1, or picture 1, I should say, you look at him, he's standing on the starting blocks, he's not moving, we're assuming his velocity is 0. So if you take any number times 0 for momentum, his momentum will be 0. In the second one, we're looking at what is his momentum. I already gave you the problem, but just thinking about this, his mass is the same. However, he's running considerably faster, because before he wasn't running at all. So his momentum has to be greater in picture 2, because his mass stays the same, but his velocity is much higher. And if you increase your velocity, you increase momentum. Now here we can do the math. We can prove that I'm correct, that number 2, he has more momentum. We're looking at his mass in question 1. And there's something tricky about this one. If I'm looking for mass, you're looking at m. We're going to use the second equation, m equals p divided by v. So we're going to take momentum, which is 0, because he's not moving, and we're going to divide that by 0. And if you notice in your calculator, it will tell you that you get an error. Now, obviously, we know that Usain Bolt's mass cannot be 0. And in this situation, you can't find his mass unless you were to calculate his mass when he actually has momentum. So we're going to do that in the next problem to figure out what his mass is. In picture 2, we're still looking for his mass, so we're going to use the second equation. Mass equals momentum divided by velocity. We're going to take 1,859.26 kilogram meters per second divided by 19.6 meters per second, and we will find that his mass is 94.86 kilograms. Now, later on, you'll learn that momentum can be conserved. It will not change. We can also think of it in terms of mass. His mass will not change. His mass before and after the race is about the same. So technically, even though your calculator reads an error sign, his mass in the beginning problem was 94.86 kilograms. This time we're looking at Michael Phelps, and unlike the other two pictures, these were not taken the same day, not even the same year. In the first picture, I've got Michael Phelps in one of his later races in about 2016. And in picture 2, this was taken when Michael Phelps was only about 9 years old. So if you consider yourself, think back to when you were 9 years old, and obviously your mass has changed a lot since you were younger. Michael Phelps' mass when he was younger was much, much smaller than he is now. Now, if we look at momentum and velocity, we're going to try and calculate Phelps' mass in each of these pictures. Now, my question was, in which of these pictures does Michael Phelps have more momentum? Now, I already gave you the numbers, so you can just look at them. The momentum in the first picture is close to 200, and the momentum in the second picture is only close to 33. Obviously, picture 1 has more momentum. Now, the reason for that is that his velocity is higher. 1.97 is higher than 0.6. And we also know, just using our minds, that Phelps' mass is definitely larger when he is bigger when he's grown up compared to when he's smaller in the picture that is wrapped in black. So B, we're looking for what is Phelps' mass? Mass starts with m. We're going to use our second equation. Mass equals momentum divided by velocity. His momentum is 199.36 kilogram meters per second divided by velocity, which is 1.97 meters per second. And you should get his mass to be about 101.2 kilograms. In question 2, we're doing the same thing. We're looking for mass. Mass equals momentum divided by velocity. His momentum in this one is different. It is 32.516 kilogram meters per second. His velocity is also smaller because he's a smaller person. In general, smaller individuals, like think of you when you were 9 years old, you probably couldn't run as fast as you can run now. So his velocity was only 0.6 meters per second. When you calculate this, his mass was 54.19 kilograms, which means he was about half as massive as he is now. In this problem, we're looking at Jessica Jerome, and she is a professional skier. And just like with Michael Phelps, we're looking at her when she is older, and she's actually in the Olympics. And then in the picture 2, we're looking at her when she was very, very young. As you can see, she's a lot shorter. She doesn't go as far. She doesn't go as fast. So my question is, in which of these pictures does Jessica Jerome have more velocity? Now, you can't answer this because I haven't given you the numbers, and I know you probably have a guess, but let's prove it through math. So B, what is Jerome's velocity in each? We're looking for velocity. Velocity starts with V. We're going to use the third equation. Velocity equals momentum divided by mass. So you take 437.4 divided by 97.2 kilograms, and she should be moving forward at about 4.5 meters per second. In the second question, or the second picture, we're looking for velocity again. So we're taking her momentum divided by mass. Her momentum is 75.3 kilogram meters per second. And then her mass is 25.67 kilograms. And if you notice, her mass went down from the first picture. So her velocity is also smaller. It's 2.93 meters per second forward. Now, if you think back, this does make sense because her momentum in picture 2 is smaller because her mass is smaller and her velocity is smaller. Now, if we look back to letter A, I wanted to know, in which of these pictures does Jessica Jerome have more velocity? Here we calculated that her velocity is 2.93. In question 1, her velocity was around, I think, like 4.9. Obviously, her velocity in picture 1 was faster. Now, this is moving on to when we talked about the conservation of momentum. So I've got an example of a cannon here. And if you know anything about what conservation means, if you conserve something, it means that the amount you have in the beginning, you want to keep it the same. Like if you have, say you have a jug of water in the desert, if you're conserving your water, you want your amount of water to stay as close to the same as the beginning as to how much you have in the end. So the number we have for momentum in the beginning before he lights the cannon should be equal to the amount of momentum we have even after the cannonball has left the cannon. But when we talk about the end momentum, we're talking about the momentum of the cannon plus or added to the momentum of the cannonball. So my question was, what's the starting momentum? Now, if you look, when he lights this cannon, the cannon is not moving at all. And if you're not moving, you have a velocity of 0. And if you look at our equation, we're calculating momentum. Momentum is P. P equals m, or mass, times v, or velocity. You multiply any number by 0 for velocity, and your momentum will always be 0. That's our starting momentum. Now my next question says, why does the cannon not have the same velocity as the ball? So if you look at this picture, the cannonball is obviously moving a lot faster. Now the answer for this has to deal with Newton's second law of motion, that force equals mass times acceleration. You look at the cannonball, it obviously has a much smaller mass than the cannon. So since it has a smaller mass compared to the cannon, it needs less force to be able to accelerate. And think back to even Newton's third law. For every action force, there is a reaction force, which means the force on the cannon and the cannonball has to be the same. But the masses are different, meaning that the acceleration is also different. You have a smaller mass, you have a bigger acceleration in terms of the cannon to the left, which is why the cannon accelerates very slowly because it's extremely heavy. It has a ton of mass. Now thinking back in terms of this with conservation of momentum, The starting momentum was 0 because the cannon is not moving. The ending momentum, if you conserve or you keep the amount the same, the ending momentum has to be 0, which is why the cannon has to move backwards. So if it's moving to the left, its momentum is negative, and its velocity is also negative, which is what we're going to work on next. So these are a couple problems we worked on in class. We're looking at football players, and on the left side, you were given that the football player's velocity is 5 meters per second. Now, if he's moving to the right, he has to have a positive velocity, so that's why I put a little plus sign in front. His mass is 100 kilograms. The football player on the right side is moving to the left, and since he's moving to the left, that's why they have this little negative sign. Think about it like a number line. If you were at 0 and you were to move to the left of 0, every single number from there on out would be negative. And then his mass is 75 kilograms. So first thing we need to do, we got a couple things we need to calculate at the bottom. Let's just take a quick look. By the end of this, I want you to be able to calculate the velocity of both of these football players together, and I want the total momentum of the system, so both the football players together. Now we can't find momentum until we find the momentum of each of the football players, so we have to pick our equation. So if you look back in your notes, momentum is P equals mass times velocity. So you take the first football player's mass, it's 100 kilograms times 5 meters per second. Keep in mind that that 5 was positive. A positive times a positive number gives you a positive momentum, so it's 500 kilogram meters per second because he's moving to the right. The second football player is moving to the left, and his mass is 75 kilograms. His velocity is negative 4 meters per second. So you're going to multiply those together. 75 times negative 4, a positive times a negative number gives you a negative number, so it's negative 300 kilogram meters per second. And you can just double check this. It's negative because he's moving to the left. Now, if I were to find the total momentum, so that's what I calculated beneath, kind of in the middle of this picture. It says total P, like total momentum of the system equals adding them together, and that's what's in your notes. It says if you want to find the total momentum, you add your two momentums. So you take 500 kilogram meters per second plus a negative 300 kilogram meters per second. Now, I know some of you guys are thinking, well, why does she say plus a negative number? If you know that that is 500 minus 300, that's fine. But either way, if you want to double check in your calculator, you can add a negative number together. Now, if you do this correct, you should get a positive 200 kilogram meters per second. Now, using what we know about the conservation of momentum, the momentum of both of those football players before and after they collide, or before and after they hit, has to stay the same. Meaning that before it was 200 and after they hit, it still has to be 200. So we're just going to use that total momentum in the second problem. So that's why I just put it into the box. P equals 200 kilogram meters per second. Now we can't calculate velocity just yet, because velocity equals momentum divided by mass, and I don't know the mass yet, but it's something really easy to find out. If two people run into each other, their mass stays the same, because if you run into another person, your mass is not going to change. You walk away the same person with the same amount of mass. So all you have to do is add together your masses. The mass from the first football player was 100 kilograms. The mass from the second football player is 75. 100 plus 75 kilograms equals a total mass of 175 kilograms. Now we can go back and now we can find out what the velocity of both of these football players together should be. So velocity equals momentum divided by mass. The total momentum is 200 kilogram meters per second divided by the total mass is 175 kilograms, meaning that together, when those football players hit, the football player on the right side, due to his bigger mass, his bigger velocity, and his bigger momentum, is going to force the football player on the right side to move to the right. Another way we can prove this is that when you calculate this, you get a positive 1.14 meters per second. Now, if we know that that number is positive, understanding that hopefully you did your math right, if it's positive, they have to be moving to the right. And you can kind of think back in terms of reference velocity or net force. Think back, and whichever one had the greater number in terms of velocity, here we're looking at momentum. If they have the bigger momentum, you take that one's direction. 500 is bigger than 300. 500 had a direction of right, which is why our end velocity is to the right. Okay. The next problem is pretty complicated. What I like to do when I get complicated problems, I like to draw out pictures. So forgive me for my not super artistic drawings of carts, but it says that you've got a full cart moving to the east and an empty cart moving to the west. Now, I just like to put that in terms of right and left. So I've got cart 1, and that's my full cart. You see I drew some circles on top. It's stuffed with things. So cart number 1 is moving to the right. It also gives us that the mass of cart 1 is 35 kilograms, and its velocity is 2 meters per second. Now, I put a plus in front because it's moving to the right, which means it's positive velocity. Cart 2, the empty cart, is moving to the left or west. It is moving at a rate of 3 meters per second. We know it's negative because it's moving to the left. We know its mass is 10 kilograms given what the information we were given in the problem. Now, before I can calculate what it's asking in the end, it says, what's the velocity of the empty cart after the collision? I can't find that out until I go through a lot of steps to get there. Before I can get there, if I were to calculate velocity in the end, you have to think, what do I need? To find velocity, velocity is v. V equals p divided by m. So to find this, first I have to find momentum. And momentum of the whole system, meaning both of the boxes added together. We do actually know the mass, but we don't have the momentum. So we're going to have to get there first. So looking at when those two boxes hit, when they collide with each other, first thing we're going to do is find the mass because it's super easy. We're just going to add the two carts together. So we're going to add the mass of the first cart, which was 35 kilograms, plus the mass of the second cart, which is 10 kilograms, and together the total mass is 45 kilograms. Next, we're going to do the same with the momentum. And the momentum is, looking back, we took mass times velocity, and mass times velocity for the second problem, we got positive 70 kilogram meters per second for the full cart, negative 30 kilogram meters per second for the second cart because it is moving to the left. That's why you have a negative number. Add those two together, and I put that total P equals positive 70 minus, add a negative 30, and if you take 70 plus a negative 30, you get 40 kilogram meters per second. It's smaller because they're going opposite directions. Now we're going to use our total momentum for this next step. It tells us that when the two carts hit, they both should be moving to the right. Now this is similar to our football problems. The full cart has more mass, and since it has more mass, it gave us a larger momentum. It has a bigger momentum, meaning that we're going to take its direction for both of the carts. That's why the full cart ends up moving to the east, even though it runs into something moving the opposite direction. So we're going to find out what the velocity is of the second cart. In order to find that, we're taking the momentum from the entire equation. We are going to plug this in order to find what the momentum of the individual cart is. What is the full cart's momentum? So we know the mass of the full cart is already 35 kilograms. In the problem, it says after the collision, the full cart is moving east at 0.75 meters per second. So that's where I get that from. First, I'm going to find its momentum. So I'm going to take P equals m times v, and I get that the momentum of the full cart is 26.25 kilogram meters per second. So I go back, and I have to think to myself, total momentum of the system has to stay the same because momentum is always conserved. So even after those two carts hit, the momentum stays the same, meaning that the total momentum we calculated before, the 40 kilogram meters per second, won't even change even after those two carts hit and they're moving the same direction. So I know the momentum of the first cart is 26.25 because I calculated that. And you have to think, if 26.25 plus whatever the momentum is of the second cart equals 40, you can just take 40 minus 26.25 kilogram meters per second, and you're going to find that the momentum of the second cart, or the empty cart, should be 13.75 kilogram meters per second. And my work for that is on the left side of this page. So I've got to narrow it. We're going back into what is the problem asking for. It says, what is the velocity of the empty cart after the collision? Now, we know that mass does not change. We now have its momentum. Its momentum is 13.75 kilogram meters per second. We have everything we need to find velocity. So velocity starts with a v. We're going to pick our equation. It's v equals momentum divided by mass. Its momentum is 13.75 kilogram meters per second, divided by its mass, which is 10 kilograms, and we get the velocity equals 1.375 meters per second right. Now the reason we know that it's moving to the right is because you got a positive number if you do your math correctly. Okay, sometimes you need to double check that you did your math right. And you also know that since the full cart is moving to the right, obviously cart 2 also has to be moving to the right. All right, this one's a little bit more simple if that last one confused you. So I've got a picture here. It says that a dog is sitting inside of a canoe, and the dog has a mass of 15 kilograms. The canoe, or the boat that I drew, has a mass of 40 kilograms. You know that the dog jumps out. Now, in the equation, it does not say which direction the dog moves, so I just went with one direction. I'm going to say it moves to the right. Okay. So the dog is moving to the right at a velocity of 1.2 meters per second. I picked that it's positive, so I put a plus in front. Now, if you think back to Newton's third law of motion, you know that if the dog jumps off the boat, for that force, you have to have an equal and opposite force, meaning the boat has to move opposite. The boat has to move to the left, meaning that when we calculate its velocity, if it's moving to the left, it has to be a negative number. So that's just a way to make sure you're doing the math correctly and a way to double check your answer in the end. Because if you don't get a negative number, you must have done something wrong. So first thing we're going to do, we've got the mass and the velocity of the dog. Given both of those things, we can calculate the momentum of just the dog. Momentum is P. P equals m times v. So P equals mass times velocity. It's 15 kilograms times a positive 1.2 meters per second. And you would guess that the momentum of the dog, that's why it says PD, equals positive 18 kilogram meters per second. Now, if you just think through this, the dog was sitting in the boat, and the boat was not moving, meaning that the total momentum, if you have a velocity of 0, multiply any mass times the velocity of 0, the momentum will be 0. So I put this up in the top. Because the starting momentum was 0, due to conservation of momentum, the ending momentum has to be 0. So we're going to go back in. I wanted to know, what's the velocity of the canoe? We have the mass. Now we also have the whole momentum of the system. Now, if it has to be 0 for the dog and the canoe, we know the dog is 18. Now you have to think to yourself, how can I get 18 to be 0? We're going to take 18 minus 18. That gives you 0, which means that the momentum of the canoe has to be negative 18 kilogram meters per second. Now we can use this information, and now we can find velocity. Velocity equals momentum divided by mass. We figured out that the canoe has to have a negative 18 kilogram meters per second in order for the whole momentum to be 0. And we were given that the canoe already has a mass of 40 kilograms. So the velocity of the canoe equals negative 18 kilogram meters per second divided by 40 kilograms, and that should give you negative 0.45 meters per second left. The reason it's negative is because the dog pushes off to the right, and the canoe has to go equal and opposite. It has to go to the left, which is a way to double check your work. The other reason for why the velocity is smaller, you have to think back to Newton's second law, that force equals mass times acceleration. If you have a bigger mass, you need a bigger acceleration, or like a bigger force, to get it accelerating at the same speed, which is why the canoe really does not go as far or as fast as the dog, because the dog is really small. It can accelerate quickly with the same force. The next one is similar to the question we started off with. We're looking at a cannon, and when the person lifts the cannonball, the starting momentum was 0. And the reason we know this is because the cannon is not moving, it has a velocity of 0. And if you multiply any number for mass times 0 for velocity, the momentum has to be 0. So I just put that up at the top. It's really easy to just write down what you know, so you don't have to think about it later. So I say the starting momentum equals 0 kilogram meters per second. Using conservation of momentum, I know that my ending momentum has to be the same. It's got to be 0 kilogram meters per second. So we're starting off with what we know. In the equation, you were given that the cannonball's mass is 10 kilograms, and you're given that the velocity of the cannonball is 80 meters per second. So we're just going to calculate its momentum of just the cannonball. So we're going to take momentum equals mass times velocity. Momentum equals 10 kilograms times a positive 80 meters per second. Similar to the dodge problem, they did not give you directions, but we're going to assume that the cannon and the cannonball, due to Newton's third law of action and reaction, have to move opposite directions. So I just picked that the cannonball is moving to the right. So that's why the momentum is going to be positive. It's 800 kilogram meters per second. Now the cannon, it asks you what's the velocity of the cannon when it recoils. Recoil means when it the reaction force causes it to move backwards. Back is in left, so negative. So the mass is 800 kilograms, which is 80 times more massive than the cannonball. And I need to know its velocity. Now, you know that the velocity of the entire system has to be 0. And when I say system, that means the cannonball plus the cannon's momentum. Now, the cannonball has a momentum of 800. You have to think, how can I get that to be 0? Because the total system has to have a momentum of 0. Now, 800 minus 800 gives you 0. So you know that the momentum has to be negative 800 kilogram meters per second. So that's our second variable we needed. So now we can solve for V. V equals momentum divided by mass. V equals negative 800 kilogram meters per second divided by its mass, and its mass was 800 kilograms. And if you notice, this isn't incorrect, but the velocity is negative 1 meters per second less. Just a way to double check your math. The velocity has to be opposite due to Newton's third law of motion. It should be negative, and it also should be smaller because it has a bigger mass. The same force from that action and reaction is equal, but because it has a bigger mass, it is going to be going slower because it's the same mass, or sorry, it has the same force as the cannonball. The cannonball can accelerate a lot faster because with the same force, it has a smaller mass, it's obviously going to move a lot faster. If you have any questions, make sure you pop into my office. It's 220J. Don't forget your test is coming up in a couple days here. Let me know if you have questions, and good luck studying.